everybody. Today we're talking about the root test, another important technique for determining the convergence and divergence of infinite series. Suppose you have a series, sum n equals 1 to infinity a sub n. It doesn't really matter if it starts at n equals 1 or 0 or some other value. The initial terms of a series don't affect the series convergence or divergence. The idea of the root test is to look at the nth root of the general term. We take absolute values first, so we don't worry about pluses and minuses. And we consider what happens as n goes to infinity. If that settles down to a value L less than 1, then the series converges absolutely, and therefore converges. On the other hand, if it settles down to a value L greater than 1, or if the limit is infinity, then the series diverges. If that limit is 1 exactly, then the test is inconclusive, and we need some other technique to determine whether the series converges or diverges. For example, a comparison test. Let's tackle two examples, one at a time. These are both fairly typical of the root test. Problem 1. Sum n equals 1 to infinity, 3n minus 1 over 5n plus 4 to the n. Because we have that nth power, this is a really good candidate for the root test. We take the limit as n goes to infinity of the nth root of the absolute value of this general term. Now, as n gets large, the entire fraction, 3n minus 1 over 5n plus 4, is always going to be positive. So we can ignore those absolute value signs. And then the nth root of the nth power, those things are going to undo each other. Overall, limit n goes to infinity, 3n minus 1 over 5n plus 4. And then that's going to give us 3/5. For example, by factoring n out of the top and bottom. That's less than 1, so this series converges absolutely. Therefore, it converges. Problem 2. Sum n equals 1 to infinity, n times 2 to the 3n over 10 to the n plus 1. This is another good candidate for the root test. I've got a lot of n exponents. Also, notice all the products, quotients, and powers in this general term an. So, again, we take the limit n to infinity of the nth root of the absolute value of the general term. We'd like to simplify this. The 2 to the 3n and the 10 to the n plus 1 aren't quite in the right form. So let's rewrite those. 2 to the 3n is 2 to the third to the n, so 8 to the n. And 10 to the n plus 1 is 10 times 10 to the n. I'm also getting rid of the absolute values here. Everything's positive, so I don't need any of that. Now, the nth root of 8 to the n over 10 to the n is just going to be 8/10. So let's pull that out. Now I have to deal with the limit as n goes to infinity of the nth root of n over 10. And I'm going to look at the numerator and denominator separately. How do we do the limit as n goes to infinity of the nth root of n, and the limit as n goes to infinity of the nth root of 10? Well, let's consider them one at a time. And let's actually be a bit more general. Let's not worry about the nth root of 10. Let's just look at the nth root of c, where c is some positive constant. All right, so when I see the nth root of c, I'm thinking of c to the 1 over n. And as n goes to infinity, I'm getting c to the 0, which is just going to be 1. So that first limit's fairly simple. What about the limit as n goes to infinity of the nth root of n? I'm again thinking of it as n to the 1 over n. Here, however, I'm getting an infinity to the 0 indeterminate form. I'm going to need to do some more work to evaluate that. Here's the trick. Instead of looking at n to the 1 over n, I'm going to look at ln of n to the 1 over n. If I can find that limit, I'll be able to get the original limit. I'm helped out by a rule of logarithms. That exponent of 1 over n comes out front as a factor. So I'm considering the limit as n goes to infinity of ln n over n. Using L'Hopital's rule, I just get 1 over n, which is going to be 0. So the natural log of n to the 1 over n goes to 0, so n to the 1 over n must be going to 1. So we've solved the problem we've been trying to solve here. The limit as n goes to infinity of n to the 1 over n is 1. That fact comes up a lot when you're doing the root test, and you really should commit that to memory. Limit as n goes to infinity, n to the 1 over n is 1. That is to say, the nth root of n is 1. Okay, now we're ready to finish this problem. Here's what we have so far. The limit of the nth root of the absolute value of an is 4/5 times the ratio of these two limits. The top limit is going to be 1, and the bottom limit is also going to be 1. So overall, we're just getting 4/5. That's less than 1, and therefore this series converges absolutely by the root test, and therefore it converges.